Tonight's video is going to be on stars. The reason is I feel like if you learn about stars, because if you think about it, you learn about the hottest spaces and learn what mass does in those spaces. Everything else is kind of easy from there because everything else you just have less and less stuff. So, you can learn your reactions from there. But if you learn about what goes in a star, that's going to help you really understand the rest of space-time as well, including the vacuum. To begin with, the sun, 93 million miles away, one solar mass, it's perhaps 1 million miles around or so. It's one astronomical unit, they call it, from Earth. What's going on deep in that core of that star is when you have a lot of pressure, like more than we can do here on Earth, but I mean a lot of pressure, you can begin to change symmetry with atoms, okay? And what happens is, under the weight of this gravity, right, this collapse weight of this gravity, all right, it's all accelerating. It's like, the easiest way to explain it is, if I'm in a rest mass, I'm sitting on the couch, I can perhaps take up space. You can't take my space without some force. But if I run across the room and bump into you, that's a lot more force. So gravity does that because it accelerates. And see, what ends up happening in this core of this star is that protons, okay, which have a repulsion, right? They all obey the Pauli exclusion principle, okay? They have charges and so forth. They can't just be pushed into each other's spaces without releasing a lot of energy. And so what happens is you have this type of hydrogen, call it hydrogen 1, okay, because the type they use here for nukes is like hydrogen 2 or whatever, but hydrogen 1, and these protons are going to join into each other's spaces, and what you're going to end up with is 2 photons will join, you release a positron and a neutrino. That we know for certain. And remember, all this stuff is trapped, so it's not like when these particles release this energy, it's not like the energy just goes away. It has to tunnel through the rest of the star. So you're going to release a positron and a neutrino. You're going to end up with deuterium. You're going to end up with a hydrogen isotope. And then you have some energy there as well. When this deuterium joins with another proton, okay, it's going to release a gamma ray, all right? And when it does that, you're going to get a heavier nuclei, all right? And this helium-3, what happens is they end up getting forced into each other's spaces, right? And you'll end up with helium-4, but it'll drop 2 protons back into the core. So it just repeats the process. It's like, even like something like a pressure cooker. If you think about a pressure cooker, if you just were able to keep adding heat and keep adding heat and keep adding heat and have it not blow, you'd be changing the symmetry of everything inside the pot, right? So really, you could look at this really basically. You have one solar mass, you have a fusion core, you're going to be pushing hydrogen protons into each other's spaces, right? When you do, you're going to get a positron and a neutrino, right? And you're going to end up with a heavier nuclei. You're going to end up with an isotope, right? So now you'll have deuterium, right? But this deuterium is also stuck, right? So this deuterium will get pushed into a proton, right? And as that happens, now it's going to release a gamma ray, right? Because now this thing is just buzzing with energy, right? So it releases a gamma ray. And we know energy is always conserved. So anytime there's a change in symmetry like that, there'll be some energy released. It's always equal mass, energy, mass, energy. This is how they are able to calculate all this stuff. So anyway, when this thing releases a gamma ray, it's a high energy photon, right? Gamma rays, nuclear radiation, you've probably heard of it. Well, it'll release this, and again, it's on a level like you're talking trillions and trillions of these are happening at the same time. So that's a lot of energy, you know what I mean? And now those gamma rays are going to have to tunnel through the different layers of the sun. The photosphere, I believe it's like the chronosphere, photosphere. You know, you'll actually on the edge of the star, you'll see what's called spicules, all right, and they look like wavy lines. And then you'll also see granules. They're gigantic lake-like waves of gas. And of course, this stuff is always pushed out of the way by magnetic fields. You know, when magnetic fields come through, they can displace stuff. Like gas will ride along the edge of that charge, because when you get a magnetic field, you also get an electric field, right? Well, anyway, at CERN, what they're working on doing is using several different magnetic fields at the same time, because what you run into for a problem for fusion here on Earth is that, number one, that temperature. All right, like the sun, I think, is like 15 million degrees or whatever. You need like 40 million degrees to do fusion here. The problem is that the temperature, right? Because you run into a containment problem because it melts everything. And then you also run into a time issue because you can't keep those particles that close together for too long, or else they just come apart. And that's the whole issue with fusion stuff here, is that we don't have enough time. We can't keep them together for enough time. You need about a second to start a really good fusion reaction. But anyway, yeah, the fusion that goes on in the sun and the fusion that goes on here with nukes and things like that is a little bit different. And really, if you've seen the periodic table of elements, you know that atomic nuclei, atoms, they get heavier as they go up. And you got more and more protons and neutrons and more electrons to match. Electrons are a weird thing because they're quantum. They're so quantum because they take up different orbitals. And like you can get this, I forget, it's like S2 orbital, S1, S2 orbital. All right. And what happens is they'll either be like inside the proton, around the proton, far out from the proton, and then they'll actually start to get these like weird shapes, you know, where they'll spit off all four sides and things like that when the atoms get really, really, really excited. But yeah, I made that mistake on the beta decay, just like mixing up my terminology, you know, because now what I talk about now is star collapse. Just to give everybody, you know, a good night sleep, our sun is not in any danger of collapse, and it's going to take a long time for that process to happen. And over those billions of years, it's going to puff up into a red giant, right? The good thing is it doesn't have a lot of mass. It's only got the one solar mass. So when it collapses, it's going to be pretty gentle, and it will turn into a crystalline lattice. You get a white dwarf, all right, which is like something small